Now, it can take some time to get used to all of the shorthand notations that we saw in the previous video. So a good exercise is to play around with some small examples where we're not overwhelmed by the other things that might be happening in a program and really just focus on the computation that's being performed on certain variables. So below are 3 little code snippets where some double variables are defined and computations are done with these variables. What I think is a good exercise is to look at each snippet and determine, at the end of this block of code, what would I expect the value to be in any or all of the variables that are mentioned. So in the end, what do I think is the value that's being stored in the variable A? After executing this block of code, what are the values that I believed are stored in the values of B and C? And after this block of code, what values do I believe are stored in the variables D and B? Take a moment, stop and think about it. Truly make a prediction for what you think is stored in each of these values, and then press play, and I'll go over the answers. Okay, the answers are, after the first block of code, the variable A contains the value 7.5. The variable B contains the value of 3. The variable C contains the value negative 1.2. And the variable D is 81. Following along with the first block of code, A takes on an initial value of 1.75. We subsequently add 2 to the value of A, going from 1.75 to 3.75. And then the third line of code takes that current value within A, 3.75, and multiplies by 2. Ultimately, this gives us a value of 7.5. In the second block of code, the double B is declared and assigned a value of 3.0. We then create the double C and assign it an initial value of negative 4.2. The third line of code takes the value within C and adds to it the value within B, ultimately storing the updated result inside the value for C. This is why the value of B is 3. The value within B has never changed throughout this block of code, while the value within C began as negative 4.2 and then increased by 3, resulting in a value of negative 1.2. The last chunk of code is a little bit difficult. Here we've initialized the variable D to take on the value stored within B, which we just determined to be 3. And this last line of code, which I agree is actually difficult to read and should probably be written in a different way, takes the value within D, multiplies it by itself, and multiplies it by itself. So just this portion on the right takes on the value of 3 times 3 times 3, which is 27. However, the entire expression would be equivalent to D is the signed value of 27 multiplied by the previous value within D, which is the same as B, or 3. So altogether, this is truly 4 copies of D being multiplied together, 4 copies of 3 multiplied together. 81 is the value that is then assigned to the variable D. It's important as we program, whenever we're reading code or writing our own, to have predictions in our mind about what we think is supposed to be done by the computer program before we hit compile. That way, we have a sanity check on what we mean for the computer to be doing and what it's actually doing to help us try to debug and make our programs as perfect as possible. Now, there's one last thing I'd like to warn you about with double arithmetic and the way that a computer internally represents doubles. Decimals come in sort of 2 forms. The finite decimals, which eventually terminate and only contain so many digits, examples like 1.5 or 2.75, those are terminal decimals, and in many ways we think that they can be stored exactly. However, other decimals go on forever, like 1/3, which is 0.33333, so on and so forth. Remember that computers are very finite things, and those storage lockers can only hold so much. This means that if we're using a computer to try to represent a number like 1/3, it cannot possibly contain all threes forever and ever. At some point, the computer is going to truncate those infinitely repeating threes, and the computer will internally just be thinking of 1/3 as 0.33333 with something like 32 threes following the decimal. What this could mean is that if I am asking the computer to check whether or not the value it has stored within a particular variable is exactly equal to 1/3, the computer might tell us that it's not. So in general, it is a very bad programming practice to check whether or not two doubles are equal to one another. Again, this is because we might know on pencil and paper that two values are exactly equal, but what you're asking a computer to do is compare its internal approximations for very exact numbers with one another, and mistakes might be happening somewhere in that 31st decimal place, and we may not be able to see such a thing. So this can lead us to having counterintuitive results running within a program. That type of error might be something that's very predictable to you, and so you might think to yourself, okay, cool, if I'm working with decimals that I know for a fact aren't exact representations of things in the real world, like pi or 1/3, then I won't check for equality. But surely, if I'm checking if a variable is equal to 1.5, we can go ahead and check with equality. And I'd like to warn you and caution you not even to do that, because there are some errors that come up in programming that are totally unpredictable that come from trying to compare the exactness of doubles. So I'd like to show you one of those examples just to demonstrate the caution that we need to have moving forward. And there actually is a reasonable explanation why this example, which is so surprising at first, is actually understandable from the computer's perspective. So let's take a look at that. I'm going to begin by creating two double variables called x and y for simplicity's sake. So I have a double x that is going to be equal to the decimal number 0.1. I'm going to have a variable y, which is equal to 0.3. And we know without a doubt mathematically that 3 times x is equal to y. Now everything here is a finitely represented decimal, so it might seem perfectly okay to check whether or not 3 times x is equal to y, and we might think the computer can get that correct. But let's see what happens when we do that. Now I'm going to use a bit of syntax you haven't seen yet, and for that I apologize, but I hope you'll be able to follow the spirit of the program. I am going to check if 3 times x is equal to y. Then I'm going to ask the computer to say yes, those values are equal. Otherwise, I'm going to have the computer tell us no, they are not the same. So altogether, we've created two variables, x and y. We know the relationship between those variables is that 3 times x is equal to y. And then we're going to ask the computer whether or not that's true. If it is true, tell us it's true. If it's not true, tell us it's false. And see what happens when I run this program. The computer says, no, they are not the same. It does not think that 3 times 0.1 is equal to 0.3. And this is a problem of comparing doubles for equality, even though these fractions are finite fractions. I should mention that this is not a C++ problem. This problem is a computer problem. It doesn't matter if you're using C++, Java, Python, any other programming language that exists. It doesn't matter if you're on a Mac or a PC. Your computer is going to get this problem wrong every single time, and other surprising ones like it. There is a reason, it's understandable and interesting, and is the subject of the next video.